Here we go. It's all yours.
All right, can you see my screen?
Yes. We got
Cool. Hello, everyone. Um, Welcome back. Welcome if you're just joining. Um, and welcome to those watching the recording on YouTube. This is Analyzing Baseball Data with our book club with the data science learning community. And this week we're going to discuss catcher framing, chapter 7 in the book. Um, it was pretty I guess straightforward in the progression of going from uh, plotting a strike zone to building up to modeling catcher framing. So that's what we'll hope to get out of this week, um, and maybe have some discussion along the way. All right. So this is directly from the book. Historically, scouts and coaches insisted that certain catchers had the ability to frame pitches for umpires. The idea that the way that they received the ball, that they could basically trick the umpire into believing that a ball was considered a strike, even if it was technically outside of the strike zone. Um, but part of the issue, we didn't have this pitch tracking data until the mid 2000s. So with Pitch FX, we were able to gain that insight, and some of the earlier sabermetricians developed some models and some statistics on how to evaluate catchers for their ability to frame. Um, so Pitch FX, that was the original pitch tracking data. Um, and then, of course, now we're using StatCast, which still tracks the ball, but it uses radar technology. Um, I'm not sure if anyone got to look at some of the supporting material, um, but I really like Ben Lindbergh's article from Grantland. He paints it's an in-depth article, and he goes and explains like the history of pitch framing and why it's so valuable. And some of these were examples included in the article. Here we have Molina on Tampa catching a pitch, as well as Domit, and it's the same location. The top one is called a strike. Uh, Molina is one of the best, or at least at the time was one of the best pitch framers, while Domit was pretty poor at pitch framing. Um, so yeah, one was called a strike, one was called a ball. You can see uh, the way Molina catches it, his arm he doesn't move very much. While some of the movement from Domit might be causing uh, the umpire to give him a bad call or uh, unfavorable call, I should say. And so this pitch is even closer to being the same. The camera angle on the second one is a little bit off, but here again, you can see uh, what a difference just catching the ball can make. So I really thought the um, comparison and the GIFs included were really helpful. Um, and of course, this is all due to the umpire's perception of where the ball crosses the plate. Of course, if we go to an automatic ball and strike system, which there are rumors of. This would pretty much wipe out the entire concept of pitch framing. So enjoy it while you can. This is one of my favorite parts of baseball. Any comments or questions about pitch framing? All right. Yeah, I think that was okay. So in the book, we get data from 2022, and I think they link to chapter 12 to show you how to get a full season's worth of Statcast data. And like Ron said earlier, just make sure that you have the latest version of Baseball R, because there's new data available, and that breaks one of the previous versions of the functions. So we gather all the data, and we basically say what the outcome is, whether it's a ball or swing or called strike, and then what the count is, and if it's the bottom of the inning or the top of the inning. And then given that, the pitch framing, we're really focused on when a pitch is taken. So we're not looking at swings and misses. We want to look at when the umpire has the ability to call a ball or a strike. So we filter out any swings, and then we gather some information on the pitch as well, where it crosses the plate, how the height of the pitch, as well as some of the other attributes. So where is the strike zone? So according to the MLB rule book, only part of the ball needs to cross home plate to be a strike. Home plate is 17 inches wide, and the ball's circumference is 9 inches. So the outside edges of the strike zone vary by plus or minus, almost 1 foot. And then it also depends on the batter's height, or I should say their perceived height, because it might depend on what their stance looks like. So the height of the strike zone is defined as the midpoint between the top of the shoulders and the top of the pants, down to the hollow beneath the kneecap. So yeah, I'm not sure if we're as worried as much about the tops and bottom of the strike zone, but that's something to keep in mind. And I think, like, if you've been following baseball, I think this definition has changed over time, but it's still been roughly the same, I think. So we define the strike zone as we define the plate width And then we add the ball as well, since it can touch the edges. And then yeah, I think they add some constant for the y min and the y max. And so from the data we had earlier, from the taken calls, we get a sample of 2000 pitches and plot it just to see what where the called strikes are and the balls. So on the surface, I would say that this is, pretty solid. You can see some called strikes maybe on the inside edge, maybe out here as well, or down below. But yeah, overall, not too bad, at least for this random sample. And then the first exercise or we do by zones. We take a look at the edges, the top, bottom, right and left edges, and calculate the percent strikes by each zone. And this is the plot that we get. This is like, I guess, somewhat useful. You can see, like, outside of the strike zone, it's a very small percentage chance that it gets called a strike. And then you can see inside the zone is much higher. But that's looking at, a large area. So there's not as much use for that. Any questions on the strike zone? Okay. Apologies if there's background noise. I feel like Zoom is filtering it out, but there's some background noise over here. All right. So 7.5, we'll be kind of taking that concept that we just talked about and oh sweet, sorry, just catching up on the chat. Yeah, Ben Lindbergh, the author and host on Effectively Wild, mentioned Ryan Dillman again recently. Yeah, I think I did catch that on one of the recent episodes, and thanks, Ron. No noise heard. Great. So there's limited use of the by zone. What would really help is to build a model so you can get like every part of the strike zone, and then take that model and like predict based on that. So we'll use a generalized additive model, or a GAM, and we'll use the binomial family. So we're basically modeling a called strike based on the location, the X and Z axis. And then we'll take our model and then using the Broom package, we'll predict the response. And then this is that plotted with 10,000 discrete points. Any comments or any questions so far?
Only comment I will also say is don't forget about that CRC blue. It's not defined in the package, but it's defined in the book. I just been changing it to regular blue as I go through and run it. Doesn't seem to make that much of a difference. If you're kind of,
Yeah,
yeah.
good point. Good point. So this is discrete. The next step taken in the book is building a continuous grid. So here we build a 100 by 100 grid representing the X and the Z. And then we take that same model and basically do the same thing, predicting the response. And here, instead of all the discrete locations, we now have this grid effect instead. And so now it might be a little more clear, like where the actual strike zone is. Yeah, it's definitely interesting. Like how I'm sure the height is based on the different heights of the batters. These ones on the edge that can be, where a catcher can really make a difference on if these get called balls or strikes. So the first scam, we only used the pitch location. Batter and pitcher handedness may also have effect, even though it's not like there's nothing in the rule book reflecting the strike zone with batter handedness. It does have an effect, and we'll show it here. So we add handedness for the pitcher and the handedness for the batter to our original GAM, and we'll have it be the hand model. And so we create another grid, and we predict the responses based off the hand model. The book, I think the book plots like a facet plot with all four different types. I think right on right, right on left, and then left on left and left on right. But they also take the difference and then put it into one plot. And so I think here is, if I understood this correctly, like this is a percentage difference. I think handedness can have an effect on the probability of a called strike. If I understood that correctly. So it could be as much as like, 2% around the edges of the strike zone, depending on the handedness of the batter and pitcher. I think I see a comment. Yeah, that would be cool. Derek says, imagine making these ggplot products for each umpire. I know there's the umpire scorecard that we might have mentioned last week, but I'm not sure if they have um, quite the same plots or models. I would imagine it's maybe similar. Um, I don't believe in this chapter that we end up adding the umpires into any of the models. I think it's mostly batter, pitcher, catcher data. But I think like that would also be another um, good effect to add for these models. But yeah, I think I'll have to check out the faceted plot too, because like it'd be cool to just see batter handedness versus like pitcher handedness. Um, but yeah, that's 2% doesn't seem like a lot, but I think on the edges it can add up. All right, I'll pause again for any comments or questions. Okay, so the final section and I guess the meat of the chapter is we actually get into the catcher framing. Um, so uh, here we get a data frame of taken pitches and predict strike probabilities. Um, here is where we get into a bit of the gory math. Um, so the uh, the model is based on a generalized linear mixed model. Um, and so we have P of J is the probability of a strike for a given pitch. Um, wait, is that correct? Oh, sweet. Thank you, Ricardo. Added the faceted image in the comments. So check that out. Um,
Called strike, but yeah,
called strike for P of J.
yeah.
Okay. Um, and then this is our strike probability here that we calculate. And then uh, alpha, I believe, uh, those are the fixed effects from the catcher.
The random
Um,
effects for the catcher, yeah.
and then if we go, so this is in the slides, but I'm just gonna add it to the comments as well here because I think it's helpful for further understanding um, this model is based on Judge Pavlidis Brooks in 2015. They moved from with or without you model to this mixed model approach. And so this is the article introducing the new mixed model, which they call called strikes above average. And then they go into the background. I won't read this all, but this is also a good introduction into the mixed model that they introduce. Um, they talk about uh, a basic equation for a line, which you may be familiar with, y equals mx plus b. And then they introduce the concept of the air term, um, linear regression assumes that these collective errors are not only zero sum, but also independent from one another. However, this additional assumption is sorely tested in sports modeling. There is a great deal of interdependence in baseball events. The same batters face the same pitchers, with the pitches received by overlapping catchers, all while having balls and strikes called by a rotating stable of umpires. These events are not independent. Interactions aside, we have hundreds or thousands of in-game events involving each player. So mixed models, however, have a place for these interrelated error terms. They're called random effects. They're distinguished from fixed effects, which are the ordinary X variables you see in your typical line equation. So yeah, the categories of count, hiddenness are therefore fixed effects. On the other hand, we can model the random effects as well. All right, so I'll leave that article for y'all to read if you want further information. Hopefully that helped a little bit. So we use the LME4 package to use the generalized linear model function. And here, Ron, you're saying this was Fielder 2.
Yeah, you have to change that to fielder 2 in that random effect because fielder 2.1 doesn't seem to exist anymore.
Okay,
Unless I made some other mistake, but it does work with fielder 2, so.
gotcha. That works for me. And that, or did you have to change it up further up too? Is that anyway?
Wherever it appears, I can't remember, but yeah, wherever it appears.
Yeah, okay. So here we build the model, and this is just using the catcher as the effects. And they come up with the fixed effects and the correlation. And I'm gonna go over to the book for a moment because I forget. I forgot what these represented. Did they say what these numbers actually meant?
Well, I mean, I can't remember what they said, but the intercept. So remember what you're doing here. You're fitting a line, um, and then the line goes through this like logistic transformation, right? That log p or 1 - p. So you're actually fitting a line to like the log odds, and so the line, the b0 is -4, right? The beta 1 is 7.67 in this fit. Those are pretty
Okay.
straightforward.
Okay.
What's the other thing? Well, the alpha is a random effect. So what you actually get when you ask for the varichords, in this case, there's only one, you get the standard deviation of the random effect. So each catcher, it's as if each catcher's effect was drawn from a random distribution with that standard deviation, the catcher's random effect. And then you can get the individual random, the actual random effects for each catcher too, if you want to. I think it's called ranf as the function you call in the fit to get that to pull out. But I think, does he actually do that? I
Oh
can't
yeah,
remember.
that's
Yeah,
what
there it is. Yeah,
this.
ranf. So he
Okay.
doesn't care. A lot of times you don't care about the individual random effects. You actually only care about that standard deviation to see what the scale, or something you don't care about either one. You're just trying to control for it. You want to make sure it's controlled for. But in this case, what we actually care about is the random effects, the estimation for each catcher's effect, essentially.
Okay.
But it's treated as if it's random, so it's zero has a zero normal, but it has a standard deviation of 0.218. But each catcher will have a different draw, as it were, from that, and it's fit. The actual draw that they get is fit to the model. I don't know if that explanation was very helpful, but that's what the interpretation is.
Um, that is helpful. Um, so that wait, this is that alpha value or do I?
No, it's a standard deviation of the alpha value.
Okay,
Yeah.
okay, I gotcha.
The actual alpha values are what he actually calls in the book delta 1 through delta B. Oh, right. Individual, yeah.
So
Sorry,
and
not the
that's
not the not the catchers. Yeah, the catchers, yeah. Yeah. I'm looking forward to another when he does the pitchers, the batters as well. But yeah, that's for each catcher.
okay. Um, so yeah, this is the next part is taking the model and extracting the random effects from each catcher.
Yeah, so it's the effect from each catcher, right?
C
Yeah,
effects.
yeah. And they just does some
Um,
stuff to massage them, but
and then uh, I think it was only player IDs, so they use this lookup to add the names as well.
yeah.
And here they're just adding the player names. And so based on only the catcher model, we get the top effects um, or the top receiving catchers, um, as well as um, the bottom as well. This was 2022. Um, Surprisingly, I'm not too familiar with a lot of these catchers. I guess I do know Kurt Suzuki, and he seems more like an offensive forward catcher, hitting more of a hitting catcher, so that kind of makes sense intuitively. Um, but yeah, that from Donnie Sands 0.358 all the way to negative 0.39. I guess these aren't converted into like run values or anything, but that does seem like a fairly big spread. Um, I think in Lindbergh's article, um, the the values I read, like the difference between Molina and Domit was like uh, one was saving like 30 plus runs over multiple years, and Domit was costing like 30 plus runs. So that it can definitely add up over the course of a season or multiple seasons. So this, oh,
Trevin, one point that I wanted to make, and I don't
yeah,
know, Ron, did you run this script, you know, uh, with the
Yes.
with the with the with the with the with the random effects? Because
Ye-
for some reason I didn't get that same list.
Okay, I wasn't gonna say anything because I was sure I made a mistake somewhere. But
Right.
I
Maybe
also
we
got
did
a
the same
different list.
mistake then.
I also got a different list.
Right.
What if our lists are the
interesting.
same?
Uh,
That's
is
funny.
it completely different or is it?
Yeah, no, it has seemingly nothing to do with this list at all that I could tell. Yeah.
Do you
I
have?
can I can post, mine, real quick. Okay.
Okay,
Yeah.
I was
These
gonna
are
say if
We'd
you
have to
were
these are
rerun
the
running,
that.
names. These are the names that I got, for the head, for the
Yeah.
header.
I'd have to rerun everything. But maybe I could do it.
oh wow,
Yeah.
Do those names seem familiar? Dalton Varsho. Yeah, see, these guys I know.
Uh-huh.
I I did not know my catchers at least from the 2022 season.
Well, I know Jadiel Molina, of course,
Yeah,
it's from my
Yeah,
hometown. But
yeah. Oh yeah, Alejandro
yeah,
Kirk.
but
Alejandro
I
Kirk, he's Blue Jays, right? Yeah, so there's another guy.
yeah,
Isn't he? Yeah.
but I couldn't get that list. I don't know what happened.
I'm just trying to
Maybe
rerun my
Jim
call while you're
can
talking.
can give us some pointers there.
I'm curious. Yeah, that's curious.
Yeah.
Um,
I'm trying to quickly run the
this
quick
was
one.
run on the entire 2022
Mm-hmm.
data set, right?
Correct. I mean, it's a sample that you're taking. So
Oh, that's
without,
probably oh, that's the problem. That's what it is. We just have different
yeah.
sampling.
Okay.
Okay.
Oh, that makes sense. Okay. Yeah, we didn't set the same seed or anything. So I probably have a completely different list too. That makes more
Okay.
sense.
Okay. Yeah.
I forgot
Okay.
about that part.
That explains it then. Yeah.
Yeah.
Yeah. I did see part of it was selected on a random sample. So I guess that makes sense.
Yep.
Um, oh, I'll add, yeah, Derek said, both Trinos and Suzuki were in the tail end of their MLB service. So that kind of tracks,
Mm-hmm.
which leads well into the next chapter as well.
Yeah, my list is different than yours too. So it is just because of the sample.
Chad Wallach
Yeah,
played
and
12 games.
there's no same
Okay.
number for the sample. Yeah.
Yeah. And no seed number
Yeah,
there.
it would be interesting to like build this model too, and
Mm-hmm.
or
Oh, there was a
have
seed.
like minimum.
Just to get some confidence here.
Yeah. Okay, cool. Good call out. Yeah, if you're watching at home, just know that
Get your own
it
numbers
could
every time.
potentially be different. Sweet. Did I miss any other? Just checking the comments again. Sweet. Any other comments? Cool. So we basically add on to the model that we just created, um, adding in more random effects for the batter as well as the pitcher. So we go through some of the similar steps here, showing the the variability for each random effect. We draw out the catcher effects, and similarly, um, we get a different list of catchers. Um, I guess again, you may have different catchers than the ones in the notes or in the book. Um, but this at least tracks with me, Yadier Molina being one of the top framers. Um, Suzuki is at the bottom again, so that tracks, and Trinos that kind of tracks with um, the original model as well. Um, so yeah, that's how we use modeling to um, gather the best and the worst pitch framers for catchers. Um, these only used um, batter, fielder, pitcher. You could expand on this and use and add umpire. You can add other potential effects as well, maybe home and away. I didn't get into any of the exercises at all, so I'm not sure if those were left as exercises for the reader. But yeah, I was there's one more slide. Just further reading um, all the way from the original like pitch FX era modeling for framing. This was the Lindbergh article I mentioned with the with with the GIFs, and it's a good overview. Brooks Pavlidis Judge, that's where the mixed effects models came from, or was at least based on. And then a few more articles as well. I don't think I got to see this one. Oh, we get into some Bayesian as well. So if you're a fan of that, maybe check out that article. But yeah, I'm a fan of catcher framing. It will be a little sad if and when umpires are no longer calling strikes and it's all automated with robots. So it'll be a little sad for me personally, but I think it's pretty cool that we can measure this, and this is a current skill. Any questions or comments, feelings about catcher framing or the robot umps?
I'm interested in that article about the Bayesian stuff, though, of course, because I'm a big fan. You posted these. You already put a PR in for these notes.
I need to put the pull request in, but I
Okay.
can do that
Awesome.
either later today or I'll try to get that in tomorrow.
Awesome.
And these are all linked in the final section.
Oh, they are okay.
Yeah.
I didn't realize that. The further reading section.
Yep.
Oh, I should have explored those. When I hit the further reading, that's me when I say, "Oh, time to put the book down."
This the 2017
Right.
article, this was in like a actual research paper. And they also did a Bayesian model. I didn't look at that, so it'd be interesting.
I definitely want to look at that.
But yeah, that's the chapter for this week. Glad I could present it.
Thank you, thank you.
Yeah, thank you. That was a good job. I did look at like one exercise. I looked at the home wave effect. I really couldn't see any evidence for a significant effect, so I didn't really pursue it much further. Did anybody else look at any exercises they wanted to share?
Did they?
I took a crack at the first one.
Would you,
Okay, maybe I can post it later. And
okay, yeah, that'd be great.
yeah, and I did I did a heat map of the
Oh,
results, so
very
get some visualizations, in the
cool.
oh yeah,
Always good to have the visualizations.
oh yeah, it helps a lot. Yeah.
All right. I guess any other questions or comments? We type the N, and then I'll talk a little briefly afterwards about the next session.